Assalamu alaikum, dear students. In this lecture, we will be once again discussing the inverse of matrix, but the context is somehow different. Okay. Uh, Here we have some questions. Question number 12. Here it is actually the reversal law of inverse of matrices. We have to prove it for this these special type of matrices, specific matrices. So these are two matrices, and we are supposed to find uh, whether this we are supposed to verify left hand side and right hand side they are equal. This is called the reversal law of inverse of matrices. So how can we do this? This is very simple. What we have to do, we have to find actually the inverse of matrices. You see, in our question, we are given A is equal to this and B is equal to this. Okay, we can find from this A inverse if it is non-singular, and from B we can find B inverse if it is non-singular. Yes, determinant of A is equal to 1, that's not equal to 0, it is non-singular. We will find the cofactors of A, we will find the adjoint of A. Adjoint of A, once again, I would like to repeat, it is the transpose of matrix of cofactors. Okay, so inverse of matrix A, that's equal to this. After that, we have matrix B. We will from this matrix B, we will first of all check whether this B is non-singular or not. Yes, it's non-singular. Its determinant is equal to -2, not equal to 0. So adjoint of B is equal to this. Adjoint of B, very simple. We can find its cofactors and then transpose the matrix of cofactors. So this is the adjoint of B. Now B inverse is equal to this. Okay. Now we have found A inverse and B inverse. We can find B inverse, A inverse. We will find the right hand side actually. So it's right hand side. So this is the value of the right hand side. Now the left hand side is AB whole inverse. So first of all, we have to find AB. So the product of A and B is this. Simply multiplying this row, first row with the first column, first row with the second column, we get second element. Second row with the first column, we get third element. Second row with the second column, we get this 2 element. Okay, so this is the product. For this product, we also have to find the determinant, whether it's not equal to 0 or it is equal to 0. Yes, it's -2, it's not equal to 0. So this is also non-singular matrix. If this is non-singular matrix, we will find it the cofactors of this AB, and we will transpose the matrix of cofactors. So the matrix of cofactors is like this. This is adjoint of AB. Yes, AB whole inverse is equal to 1 by determinant of AB into adjoint of AB. That's equal to this. Yes, we have. You can see from equation number first and second that these are equal. Yes, you can check. This is equation first, and this is equation number second. They're equal. So what we conclude? We conclude that AB whole inverse is equal to B inverse A inverse, and this proves the result. Another set of questions given in this exercise is based on the equations. We are given a matrix, we are given an equation. We have to first of all show that this matrix satisfies this equation. So after that, we have to find the A inverse, but we have to find A inverse from this very equation. How can we? We will check it out here. So we are given this matrix. We have to prove that A square minus 5A plus 7I is equal to 0 matrix. So it's A square is this. 5A we can calculate. 7I we can calculate. We will write it over here. And this is A square minus 5A plus 7I. That's equal to what? It's 0 matrix. We have proved this. Substituting these values in this, we see that this is equal to 0 matrix. After that, we have to find A inverse. What is the procedure for finding A inverse from this such a type of equation? We have to either pre-multiply or post-multiply this equation by A inverse. Say we will pre-multiply or post-multiply by A inverse. Say post-multiplication of A inverse. This gives A into A, this into A inverse minus 5A into A inverse is equal to minus 7I into A inverse. So this comes out to be this. A into A inverse, we know this is equal to identity matrix, and A into inverse is identity matrix. Identity matrix into A inverse is equal to 7A inverse. So A inverse is equal to minus 1 divided by 7 into its A minus pi y. So A inverse we have calculated. Now we will put the values of A and I. So this comes out to be 1 by 7, 2, 1 minus 1, 3. So A inverse we have calculated, this is equal to this one. Okay. So this is the way, this is the method how can find A inverse from given equation for which the given square matrix satisfies the given equation. Next question, very simple. It's not any hard task to do. It's question number 14. Is A is equal to this? Find the numbers and such that this is equal to 0 matrix. We have to find A square and put the values of A square, A and I in this equation. We will be getting simple linear equations, algebraic equations, and then we will find the values of A and B. So this is the way. This is the way. You see here. Okay, you can see it here. Solve with this. So A is equal to minus 4 and B is equal to 1. So it's very simple. Next is it is for matrix A is equal to this. We have to first of all show that this is equal to 0 and find A inverse. This is once again question, same as question number 13. What we have to do, we have to first of all find A cube. We have to find A square. We have to put the values of A cube, A square, A and I in this equation, and we have to prove that this is equal to 0 matrix. Yes, we can do it. After that, we'll make post multiplication by A inverse, and we will transfer all of the terms on the right hand side and keep left on the left hand side only A inverse, and we'll find its value. Yes, it's solved here. I have solved it here. It's question number 15. You see, you can find this A square, you can find this A cube. Yes, I have found it here. So the method is very important. That is how to solve the question. The calculations are very simple. After putting these values of A cube, A square, and A and I in this given equation, we see that this is equal to a 0 matrix. Yes, this is 0 matrix at the end, this one. So this is equal to 0 matrix. If this is equal to 0 matrix, after that, what we have to do? We multiply, post multiply this by A inverse, this equation. We get this, and we get A inverse is equal to minus 1 divided by 11, A square minus 6A plus pi y. We'll put the values of A square, A, I in this equation number first. We will get the value of A inverse. Yes, we will get the value of A inverse. This is the value of A inverse. So once again, question number 16 is same. Question number 17, it's now an objective type question. Let A be a non-singular square matrix of order 3 cross 3. Then adjoint of A, determinant of adjoint of A is equal. Earlier we have solved this, and you can see from the general notation earlier that in previous classes we have seen that this determinant of adjoint of A, if A is a square matrix of n cross n, the determinant of adjoint of A will be equal to determinant of A power n minus 1. So it is 3 cross 3. Here the solution is part number B, that is square. So it is now, yes, here it is. I have attempted to solve this. You can see it is determinant of A square. Next is question number 18. Question number 18, once again, an objective type question. If A is an invertible matrix of order 2, the determinant of A inverse is equal to. I have to find the determinant of A inverse. See, it is determinant of A inverse. You know the definition of A inverse. A inverse is equal to 1 by determinant of A into adjoint of A. We have to find the determinant of A inverse. Determinant of A inverse is equal to determinant of right hand side. Determinant of right hand side is equal to determinant of this. This is a scalar quantity, and here it is the determinant of adjoint of A. Determinant of adjoint of A is determinant of A, but having power 1 less. So this will be simply 1. If it is power 1 less, this will be equal to this will be equal to 1 divided by determinant of A. Okay, so the here illustration is given here. You can see this illustration. If you have any confusion in these questions, you can ask in the comment section. Thank you for joining the class.